Welcome to part 8 of our Dueling AI self-play reinforcement learning series. So in part 8, we are going to actually start building out the self-play infrastructure. And I'm going to start with just a little bit of a conversation about the theory here before we go any further. And then the code will hopefully make a little bit more sense. So I'm just going to start typing in a README here. What we're going to be doing. So right now we have a model that is playing against a static agent. So right now you've got model versus static player. And that's a static player that we coded up in a previous video. And the model will slowly get better against that static player. And what you end up with is performance that looks something like this. If you don't have this level of performance at this point, if you're not in a place where your model is learning somewhat, at least up to scoring, 9, 10 in the first 500 episodes against the static EasyBot, then now's a good time. Go back to the previous video, look at the checkpoints, make sure this is all working before you go any further. So right now we have model versus static player. And what we're going to move towards is we're going to move towards a stable of checkpoint models. So we'll say checkpoints. Again, I'm just typing things out to explain. You don't have to actually code this part. So we'll say we've got a model V1, and then current model is also V1. So we're going to immediately copy our current model to our checkpoint model when we first start. Now, at some point, we are going 100 episodes in. We're going to do this every 100 episodes. We're going to create a V2 model. And if that V2 model is, as good as the V1 model or better, then we're going to check V2 into our checkpoints. And what we'll have is basically a loop. So in our loop, we're going to choose checkpoint and then play current model versus checkpoint. So for every run of our training loop, instead of playing the current model against a static player, we're going to play the current model against one of the checkpoint models. As we go, so let's say our V3 is a little bit better than V2, we're going to check V3 into our checkpoints. And then at some point, we'll have a max length for checkpoints. And let's say our max length is 3, just for the sake of this demo. We'll have our 3 checkpoints. And when it's time to cut V4, let's say that V4 is better than V1. It's the best one, and V1 is the worst. Again, hypothetically. We're now going to have our list of checkpoints will be V2, V3, and V4. And we'll have a couple of safeties in place. So the two things we're going to do is we will be implementing a custom checkpoint pool class that is smart enough to reject anything that does not have a score that's at least as good as the previous scores. And then we'll also be doing a check in the training loop that looks for only the top scores. And when we have a new best score, we will check that in. And what we're trying to avoid here is we're trying to avoid clustering all of the models around whatever the latest thing is. Our goal here isn't just to have the best models in checkpoint, but to have the most diverse set of models. In this scenario, we want the previous copies of the model to be able to be a diverse set of opponents that our current model can train against so that it doesn't get pigeonholed into one strategy that works against one model. If you don't do this, if you either just play the current model against itself, what you end up with is you actually end up with a falling performance curve. So the model will learn how to exploit something against itself, and then it will actually get worse over time as it overfits to its own vulnerabilities. So what you want is a large stable of previous models You want to keep your checkpoints out of circulation, out of being the thing that's being trained. You never want to train your current model against something that's too close to itself for too long. And I know this because when I experimented with this the first time, my initial strategy was to just say, hey, model, play against yourself and train against yourself. And it ended up not being a stable enough opponent to learn against. It ended up exploiting its own, flaws and then going into a death spiral of performance that wasn't great for what I was trying to accomplish. So this checkpoint pool works pretty well. Let's talk about the one other thing that we're going to need to add architecturally. So we need a way to judge performance objectively, or as objectively as we can. You can't really say, because if everything's working correctly, what you should see is you should see that these scores kind of hover around 0. You'll see, the checkpoint models getting better for a little bit. You'll see this drop down, and then this will get better against the checkpoint. And then you'll see a little bit of a wave up and down. But that also means that you can't really tell whether a model is better than a previous one programmatically very easily. It can be unstable. So what we're also going to do is we're going to build an eval function. So every X number of loops, we're going to call eval. And eval is going to play a certain number of games against our static opponents that we built earlier. So it'll play, for the first few hundred loops, it'll play against the easy bot, and then it'll play exclusively against the hard bot. And that's going to give us something that is a much cleaner way to track performance, because again, this is going to bounce all over the place because it's playing against itself. You can't really tell how good it's doing. You can just tell how well it's doing versus previous copies. But using an eval function, that's going to allow us to actually track, hey, you're getting better against some objective opponent. And an important part of the experiment that we're doing here is that we're not including training data from those objective opponents. So the idea is we are training only against our own data, and then we are testing only against our external opponent, which should confirm that our agent is learning generalized skills, because that's really the promise of self-play and reinforcement learning. That's the thing that we're trying to get to, is the idea that the agent should, through only playing against itself, be able to learn generalized skills that work against any opponent. And that is our objective. And you'll actually see that with self-play, we will achieve better, faster results than this score of 9. We're going to easily hit, 20 against the easy bot. And we'll get decent scores, low single digit, but that's fine for what it is, against the hard bot. So with that, let's go ahead and jump in and start coding. So we're going to add a new file, and this will be checkpoint.py. And I'm going to set the width a little lower here. All right, there we go. That gives us a little bit more screen real estate to play with. We're going to import copy, random, and torch. And then from collections, we're going to import deck. Our class is going to be checkpoint pool. And we'll need a couple things. So we're going to define our init method, and we will take in self, max size, and max size is going to default to 5. That'll be our initial number of checkpoints that we're saving. So we'll say self.maxSize is equal to max size. And then the pool itself is going to be a deck of tuple float torch.nn.module is equal to deck. All right. We will have an add method. So def add self model score. So we're going to pass in a score. And again, this score is going to be based on its performance against one of our static models. That's the best way that we can get an objective score over time. So self.pool.append score, and then copy.deepCopy model. I'm going to make sure we're actually getting a copy. Self.pool, it will be deck, and we're going to sort self.pool. Oh, I got too many curly braces there. Self.pool, and for our key, we are going to have lambda x, the 0th element, and reverse equals true. Okay. And then we will trim the worst member of our pool here. So while length is self.pool greater than self.max size, then self.pool.pop. And this bit of functionality is important if you just used a regular deck, the oldest thing would fall off, whereas we want to make sure that the lowest score always falls off. I will say there is going to be a little bit of logic in the agent class that makes this redundant. We're going to be tracking the best, overall top score and only adding those. But this implementation does give you a little bit more flexibility if you want to play with different methods. So I'm leaving it in for that purpose. We're going to go ahead and do a sample. So def sample self, and we will say if not self.pool, then we'll raise a runtime error that basically says checkpoint pool empty. Can't pull from it if it's empty. And then we will do underscore because we don't actually need the score value. And we will do zip star self.pool. And I did not mean to put a dot there. So we're going to unpack self.pool. And then we will return random.choice models. All right, so our sample is basically just going to return a random choice from our list of models. And then we need to add a couple of helper methods. So we'll do def len self return len of self.pool. And then we are going to do def best score self, and we'll return self.pool 0, 0 if self.pool else none. All right, and then finally, and this one is optional. If you don't want to type it out, you don't have to, but it is helpful. We're going to write a quick little reporting method that'll print out some of the models that are in the pool. So def report self. We will go ahead and say if not self.pool, message is equal to checkpoint pool is empty. Print message. And actually, this can be a little bit less complicated than it was the first time I wrote it. Print checkpoint pool is empty and return. Okay. Else, if that doesn't fall through, we're going to have rows is equal to blank set, and for rank score model in enumerate self.pool start equals 1. And then we're just going to do rows.append and a little bit of formatting here, rank. And that's going to be a _7. And then we'll do another pipe there and do score _20.2 f. And then that will be the end. And then we can do header is rank skill /n. Gotta love text formatting. Plus /n dot join rows. And let's call this, first off, that should be, let's call this message plus /n. And the formatting isn't super important here, but it helps. It looks nice. So header. Nope, not heaviside. Message is what we wanted. Okay, so now we should be able to call our report method, and it should print out the current values inside checkpoint pool. So we have a checkpoint pool that we can use. Let's go back to our agent, and gonna need to set that again. All right, so inside of our agent class, we're going to need a few more things that we didn't have before. So we'll go ahead and say that our checkpoint pool, let's go ahead and define that. Actually, let's import from checkpoint, import checkpoint pool. Cool. And then down here under our target model, we will go ahead and say self.checkpointPool equals checkpoint pool. Max size is equal to checkpoint pool, because that's a variable we took in earlier. And then we'll do self.checkpointPool.add self.model with a score of -100. So why am I doing -100? The initial agent could score as badly as -20. And this is actually one of the problems I ran into when I first implemented this, is I started with, hey, I'm going to store it with a score of 0. But the thing is, that score of 0 artificially put there was better than anything else that would come after it for hundreds of episodes. So what ended up happening is nothing overrode it. It would just, that worst initial model would just kind of hang out there forever, which doesn't really do what we want it to do. So we start out with -100, and then this initial untrained model stays the lowest scoring model going forward. So we're going to say self.checkpointModel. We'll default that to none. That's not something we'll set initially. We will also need to set up some eval environments. So up here under self.env, if you recall, I said we were going to have a couple of environments to evaluate against. So here we're going to say self.eval envs is equal to, and then we'll just copy this. And then we're also going to need a second one. And we're going to leave the bot difficulties. We'll take those off. We're going to be setting that later on. But for each of these, I left out a close paren there. We'll make the first one player 1 AI and player 2 bot. And we'll make the second one player 1 bot, player 2 AI. So those are our ENVs that we're going to define. We'll also need to do a little bit of extra code here for eval mode. This will be when we're actually like really testing the model. We're going to say if self.eval mode, which should be one of our params up higher. And actually, we may, here, I think this needs to be eval mode because eval is, no, that'll be okay. If eval, then we want to go ahead and load our model. So let's find down here. Okay, so we're going to say self.model. And then we want to do self.model.load the model. Self.epsilon is 0. And go ahead and return. Okay. And the reason we're returning if we're in an eval mode is because if you go through and create these environments when you're in eval, it's actually going to spin up multiple copies of Pygame. And if you're attempting to, if you're attempting to watch a live game, you don't want 4 copies of Pygame just sitting there. It can actually overwrite some environment variables that will mess things up for you. So that's what we're doing. We're just if eval, load the model, return, and don't do the rest of this. I mean, we may have to move some things up, but we'll get to that later. Actually, yeah, frame stack is here. Frames are here. We'll need these up above. No, that seems good. That seems good. We'll find out later when it errors or doesn't error. So let's go ahead and go get down into our train method. And we're going to need a couple of things here that we didn't before. We're actually going to need to work on our get action method. So get action is here. And the first thing we're going to need to do is actually flip our observations if we're player 2. So there's a couple of different ways you can handle making the same agent play, or I'll even say a self-play scenario in general. So we could train 2 completely different agents to play both sides. And actually, let me take a minute and define the problem. So when you pass in, a human understands and can generalize very easily when looking at a game that playing one side of the game is exactly like playing the other side of the game. In general, if you're teaching a person to play chess or something, or checkers, they don't get confused if you ask them to play the other side of a chessboard or the other side of a checkers board. Most people can generalize that, flipping the board around does not make it a completely different game. Your AI can't. It's not that smart. It's not capable of going, hey, this looked different, but I can still take the concepts. It will actually get confused unless it is specifically trained on, something that tells it what side it's supposed to play. So there's a couple of ways you can do that. One method you'll find comes up in some of the documentation people write on these things is setting up an identity channel. So feeding something into the network that says, hey, player 1 or player 2, and then counting on the agent to understand that when, player 1 set and the ball goes over the left, that's a score, but over the right, it's a fail. Or when player 2 set, the opposite. My experiments with that were a little mixed. It didn't really learn well which player was which, but I also had some other issues at the time, so I'm not going to say that method couldn't work, just that it didn't end up working for this project. The other thing you can do, and what quite a few popular RL Papers cover is that you can just flip the observation. So because your Pong game is horizontally symmetrical, you can literally just flip the image and fake the agent out and make it think that it's always playing the same side. So that's exactly what we're going to do. Is in get action, we're going to flip our observation. We're going to say, hey, you always act like you're on the right. So let's go ahead and we're going to define a def flip OBS. And that is going to have one line, return torch.flip, and OBS, and dims is equal to 2. And it really is just a one-line function. The reason I am making it its own function is because this is an important enough piece of functionality that I want to let it be somewhat self-documenting. I want it to be very obvious looking at this later that we are flipping an observation. So we're going to say if player is equal to 2, obs is equal to self.flip obs. Okay. So simple enough. If we're playing player 2, flip the observation. All right. Now we need to do our checkpoint models. So we're going to say if checkpoint model, then we're going to throw a little bit of randomness in early on. So here we're going to, and actually just to make things line up the way we're going to later, I'm going to throw this whole block that we've been playing with into an else. All right, that's the way we want to land. So all of our previous logic was not checkpoint. That was, calling the standard model. So if checkpoint model, we're going to say if random.random. And we'll put that in parentheses just to be consistent. So if random.random is less than self.epsilon and episode is less than 1000. So what we want to do is we basically want to say, hey, if we're in an early episode, let's get some randomness in our checkpoints because the checkpoints aren't going to be doing anything. So it has to have some random actions or it's not going to be a good opponent to train against or even a passable opponent. So we'll say self.env.actionspace.sample. Else, then we'll basically be doing the grab those, copy them up here. But instead of self.model.forward, it's going to be self.checkpointModel.forward. And everything else should stay the same. And then down here, we're just returning action. So get action should be in a happy place now. All right, let's go back to our train method. And we need to make a couple of tweaks here. So instead of just getting player 1 action, we're going to get player 1 and player 2 action. So we can just rename that to player 2 and then pass in player equals 2. And that should be okay. And then here in our self env step, we are going to pass in player 2 action, not player 2 reward, player 2 action is equal to player 2 action. All right, that looks like it's going to be okay. And it is a little squeezed on my screen. It's a little bit of a balancing act. I'm trying to blow things up enough to where it's really easy to see at a normal YouTube resolution, but that does mean things get a little bit squished. So doing my best there. All right, so here we are now taking action as player 1. And player 2, we're getting actions for both. But we need to put a little bit of logic around which one is the checkpoint model, because we're just saying that every single time is checkpoint model false, which is not what we want. So let's go ahead And I'm going to go locate my flip code. All right, so at the very top of our train method here, we've got our best average score. Right above that, we are going to add a couple of variables. We're going to add player 1 use checkpoint is false. Player 2 use checkpoint is true. And then for every episode, every time we kick off a new episode in the range, we're going to say player 1 use checkpoint, player 2 use checkpoint equals not player 1 use checkpoint, not player 2 use checkpoint. And it is important to keep these on the same line because obviously if you split them out, then the logic is going to be a little bit backwards. But what we're doing here is we're effectively flipping every single time which player is using the checkpoint. So we start out false, true, and then we're going to flip to true, false, false, true. So it should flip back and forth as to who is the checkpoint model, player 1 versus player 2, and who is the real model. So we'll go ahead and say self.checkpointModel equals self.checkpointPool pool.sample. Okay. So we now have a checkpoint model that we can play with. This all looks good. Tighten that up a little bit. Done as false. Our episode rewards should stay the same. Our actions we've already updated. We're already calling player 2 actions. We do need to do a little bit with our store transitions. So we want to only store transitions from the active model. So what we're going to do here is we're going to say if player 1 use checkpoint, then we're going to store player 1 action, player 1 reward. Other way around. So let's just copy that and paste it because we're going to need it in a minute. So if player 1 is using the checkpoint, then we want to store the player 2 action. We want to call self.flipObs and store the flipped observation. We want player 2 reward. And then we want to call self.flipObs on next observation. So there are two places we're flipping observations. We're flipping them when we're calling the model, and then we're flipping them when we store player 2 transitions. So we're effectively tricking the training loop into thinking it's always playing as player 1, and then making it an always player 1 loop in the action selection. After we've got that, we'll throw an else in there, and that's where we're storing player 1 rewards and next observations. And this is probably a good place to run the code and see if we have any obvious errors. We're not quite functional, but we should be able to look for problems with our checkpoint. And I'm going to pause the video while it rolls through some of these. All right, so we've managed to make it through a few runs here. I'm on episode, let's see, we did not print out the episode number. We'll have to add that. Oh, no, we did. Completed episode 226. So I made it through a couple hundred episodes. It's doing about what I would expect it to so far. But we haven't done anything to actually add previous checkpoint or previous models to the checkpoint at this point. And we haven't done anything to evaluate our checkpoint models. So the next step is to actually work on our eval function. So I'm going to kill this, and we are going to build eval. So up above, let's put it above train. we're going to define eval self, and we'll pass a default bot difficulty of easy. And then we're going to say for eval env in self.eval envs, eval env dot bot difficulty equals bot difficulty. So we're basically going to just set those difficulties in the beginning of the loop. We'll have an episode reward equal to 0, 0. And then we're going to say for player in range 2 obs info equals self.eval envs player dot reset. So we're basically grabbing an eval environment from our either the 0th or our first index. We're grabbing an eval environment and setting that, grabbing obs and info from that eval environment. We'll do obs is self.process observation. And we'll go ahead and say clear stack is true, because we want a clear stack for starting our eval run. We don't want any images in that buffer. And then we'll say done is false. Episode reward player is 0. Episode steps is going to be 0. And then we'll just say while not done and episode steps less than self.max episode steps, reward equals 0. And this will look a lot like a training run, or a lot like one of our standard training episodes. And here we'll say if player is 0, then our action is going to be equal to self.getAction obs player equals 1. That's one thing I don't love about this, the way I coded this out, is, because I'm doing player in a 0th index, it ends up being a little funky right here, but it's not the worst thing in the world. And I'll pass in eval mode is true. And next obs reward done truncated info equals self.eval envs player dot step, and player 1 action is equal to player 1. Let's see, did I not get an action? Oh, I just called it action. That's the problem. So player 1 action equals action. Elif player is equal to 1, then action is equal to self.getAction obs player equals 2, eval mode equals true. And then we'll do kind of the same thing. I'm just going to come copy this because very similar. Okay, and we're just going to say player 2 action is equal to action. And if you recall, the way we built the environment is if you pass in just one player action, the other action is automatically going to default to the bot. So we don't have to manage any of that logic here, and that's why we built it that way. We'll do obs is equal to self.process observation, next obs. And then episode reward, player plus equals reward. And then finally, we're going to return episode reward 0 and episode reward 1. Okay, so we have an eval function that we can play with. So what are we going to do with that? Let's go down back into our train method, and we are going to have an eval section. All right, so down here around line 195, right under our target update interval code, we're going, oh, I made a change there. I did not mean to make, I think. All right, so tab in to the same level as writer.addScaler. And we're going to grab a couple more log items that we need here. So we want to be able to not just log player 1 versus player 2 rewards. We also want to be able to log checkpoint rewards versus our live rewards. Because remember, it's going to bounce between player 1 and player 2. Different players will be playing each time. So we want to go ahead and basically log, well, I'll just show you. We're going to say if player 1 used checkpoint, then latest reward is equal to player 2 episode reward, and checkpoint reward is equal to player 1 episode reward. Else, latest reward is equal to player 1 episode reward, and checkpoint reward is equal to player 2 episode reward. Okay. We can go ahead then and add some extra lines here. So we're going to add, copy these, and instead of training score player 1 training, we're going to have latest policy and checkpoint policy. This is definitely something I've noticed building out self-play, is that I found myself logging a lot more information because it was just a little bit more complicated to keep up with. And I ended up needing all of this in the course of building the solution. So we're going to say latest policy, latest reward, checkpoint policy will go to checkpoint reward. All right. Then we are going to need a whole eval section here. So under our checkpoint policy, we're going to say if episode greater than 0 and episode modulo 20 is equivalent to 0. So basically, if it's not the first episode and every 20th episodes from there, we're going to do print eval run started. And actually, let's do a little log header method, because we're going to end up typing this a few times and it'll just pretty it up a little bit. So let's do def log header self line print dash times 50, not 500, 50, print line, and then we'll print a closing dash times 50, and that'll put us in a good spot. All right, let's go back up to where we were. Somewhere. Here we go. All right, so instead of print eval run started, we're going to say self dot log header eval run started. Okay, we'll add some dots. To be continued. All right, and then here we're going to say eval env list will be easy, hard, if episode is less than 400, else hard. And the reason we're doing this is in the very beginning, it's really hard to see any kind of performance uplift against the hard bot, because the hard bot is really hard. It is a very difficult bot for the agent to learn against. So we're going to go ahead and include the easy bot so that we can see some early training success and see if things are working. At the same time, once we're up and running, we don't want to waste the time running a bunch of episodes against the easy bot that are just going to be maxed out. Very early in training, it can beat the easier bot pretty successfully, and it's just not useful data. Again, especially when it takes time to generate. These are not free. They take some training cycles. So for difficulty in eval env list, we're going to say player 1 score v bot, player 2 score v bot is self.eval. And I just remembered why we did not do a self.eval here, because this would have run into issues. Okay. So self.eval, and we're going to say bot difficulty is equal to difficulty. And that should be all we need there. So now we can go ahead and go writer.add scalar eval score / player 1 v difficulty bot player 1 score v bot episode. And then we're just going to copy that and say eval score player 2 vbot, and then we'll do player 2 vbot. And then just to make sure that we get something in the logs as well, I like to have both. We're just going to print player 1 v difficulty bot and player 1 score v bot, and then copy that to player 2. Okay. And then come in 1 and print eval run finished, saving the model. And we'll go ahead and self.model.save the model and print model saved. You can tell I'm a fan of logging. And then I'm also going to say self.checkpointpool.report. This is when I want it to print out how the checkpoint pool is going. And then we'll do self.logheader, and we'll say eval run complete. And I just want to, we've added a bunch of code, we've added some eval stuff, we've added a bunch of eval logging. Okay, we are not erroring. Now again, we still haven't added any code. We've got, player 1 training, player 2 training. At the 20 episode mark should be when we kick in our bot. Hey, there we get our eval score. And we've got eval scores versus easy bot and versus hard bot. All right, and the easy bot, the player 1 scores look right. The player's 2 scores don't. That should not be 0. 0 is actually a really good score against the hard bot. So that tells me that we have a problem here. Let's see what our problem is. So our eval run started. Player 1 versus EasyBot. Player 1. Okay, so yeah, those are also coming back zeros. So that is clearly not succeeding at doing a training in eval run. So we've already got player, and it's player 2 in both scenarios. So player 1 score vbot, player 2 score vbot, both calling self.eval. Let's come up here and take a look at self.eval and see what maybe we're messing up. So episode reward plus equals reward. We'll cancel that. We don't need it anymore. While not done. All right, so 4 player in range 2. Let's just start there. Okay, def eval 4 player in range 2. And it's always player 2. So there's something about the I think I see what might be going on. So here we are doing a reward for player 1, and here we are also doing a reward for player 1. So here we should flip our underscore to that reward, and let's run it again and see what we get. And by the way, if you, because you will stack up quite a few of these runs, you know, this has just been in the course of a few test runs while we've been working on the project. I probably ran this 1,000, 2,000 times while working on the project. You will not want to keep every run you've ever had. Just clear out the runs directory every once in a while. When you hit a point where you want to get rid of all that old data, clear out runs, and that'll solve the problem. Okay, we're at 14. Let's keep going. At 20, we should see our eval run kick in. And you can also start to see even now how, you know, latest and checkpoint policy data can start to be useful. Like we can see that our latest policy is already starting to get a little bit better than our checkpoint policy. And, you know, our training wouldn't really tell us this. Like player 1 versus player 2 isn't super useful for telling us how things are actually going. All right, we're still in a flat state. So player 1, let's go look at, yep, eval run complete. Player 2, we still landed in a failure there. All right, so elif, player 1, action is action. This is, something is broken here. So if player equals 1, we want to do player 2 action. We want to grab self envs. We already fixed the reward here. We're calling it with player equals 2. Like this is clearly going to be some kind of variable missing while not done. range 2. All right, I'm going to pause the video for a moment and see if I can spot the problem. All right, and it is an indentation issue. So my return statement here is inside the loop, and it needs to be outside the loop. So we're basically collecting player one's data, and then we're exiting and returning, and that is definitely not what we want to do. So let's run this one more time. And I'm again going to pause while this runs. All right, let's see how we're doing. We're not quite, yes, we have been over 20. And we can see now that player 2 versus the easy bot is 1, and player 2 versus the hard bot is -10, which is much more what I would expect. I'm also, you know what? I've been a little surprised by the -10s, where I was expecting 20. And I think it's because when we were working on the game, we set a top score to 10. So let's go ahead and hop in game.py here and change that to 20. 20 is going to give us a lot more play here. So, all right, so we've changed top score to 20. Let's go ahead and kill this. All right, and we are going to complete, we've got just a little bit more in our eval section here. So at this point, we are evaluating how our agent's doing. We're evaluating our performance over time. The last thing we need to do is we need to go ahead and set up our checkpoint pool evals. And we could bake this into the eval section, but we're not going to, or the eval loop that we just wrote. But I actually only want to update the checkpoint pool every 100 episodes. So we're going to break this out and make it a little bit different. So down here, we're going to say if episode greater than 0 and episode %20 is equal to 0. Then we'll do self.logHeader, checkpoint pool, eval run started. We'll say player v bot total. We'll set that to 0. And we'll say eval EP count is equal to 3. So we're going to run 3 eval episodes, and we're going to total up the scores, and that's going to be what we check into our checkpoint run. So we'll say for I in range, eval EP count, and we'll do player 1 score vbot, player 2 score vbot is equal to self.eval. And in this scenario, I'm only going to do bot difficulty hard. I want the objectively best model, and I don't care about, the visibility data from it. So we'll do player v bot total will be plus equals player 1 score v bot, and then copy and paste that. And we're going to say player 2 score v bot. We'll go ahead and print that. Player v bot total will be player v bot total. And player v bot average will be player v bot total divided by eval episode count times 2, because we're grabbing 2 scores every single time. So if we're doing 3 episodes, by 2, that's going to be a 6 eval count. So we're looking for the average player vbot score. And then we're going to say self.checkpointpool.add self.model player vbot average. And I actually thought I had remembered adding some code in here to only check in the absolute best models. It looks like that is not what I ended up doing. That's what happens when you iterate on a piece of code for a month. And we do up here need to say 100. That should have been 100 and not 20. I made it look a little bit too much like the code above. So every 100 episodes, we are going to add the latest model to the checkpoint by score. Again, the checkpoint pool is smart enough to only add models that are better than all previous models and then bump the worst model out of the pool. And then finally, we'll say if player v bot average is greater than best average score, then best average score is equal to player v bot average. And we're going to say self.model.save the model. And file name is equal to fmodels/model best.pt. Okay. And then we'll say saved new best model average score best average score higher than player v bot average. Okay. Else print failed to save new best model. Oh, I need an F at the beginning so that we can use variables. And we're going to say best average score higher than player one bot average. Okay. And then at the very end here, we will say self.log header, checkpoint, pool, eval, run, finished. Okay, and I need that 1 over, otherwise it's not going to log out successfully, and that will not give us what we want. Okay. I feel like this episode time is going to not, that could result in some a little bit of weirdness. But I think it'll be okay. That'll be fine. All right, let's go ahead and run this. And what we should have now is at the 100 episode mark, we should go and save our model. And you know what? Let's test this functionality just a little bit faster. Let's say that every 10 episodes, we want a checkpoint model, because I don't feel like waiting for 100 of them. And this is not the best thing for training, but it is going to be the best option for seeing if we're being successful more quickly. Okay, we've hit 8 runs. And we just started a checkpoint pool eval run. We can see we could probably do some better logging around like that this was a checkpoint episode. And that's why the episode time was 19 seconds. It does show us what we need to see though. All right, so the good news is it didn't fail on the eval run. That seems like a positive. It does say that it saved new best model. Yep, average point, score 19. That feels like okay. I think I see our logic issue there. So player V bot average. We've already set best average score to yeah. Let's do this. Player V bot average higher than best average score, and then we make that change. Otherwise, it's just going to say that, the new average is better than the new average, which is not super helpful. And we can see here that when we print out our list of models, it does have our original with a score of negative 100, and then it has our new one with a score of only negative 19.67, which sounds like things are working exactly the way they're supposed to. All right, let's change that back to 100. And this is now the time to go and run this and let it play for, an hour or so and see if it learns successfully. I am going to go ahead and end the video here because this has been an hour long already. In the next video, we're going to come back. We're going to see if this did in fact train successfully. And then we're going to integrate the successfully created models in with our Pong game so that you can watch the thing play, you can test it in real time, you can play against your own agent, and that will be the last video in the series. As always, if you need help, look in the video description. There will be a Discord link. I will also post the code as of the end of this video, so you can go take a look at that tag out on GitHub. And if all else fails, post a message in the video comments, and I will try to get you some help. So with that, I will say thank you for sticking with me for this long for this really fun little project, and until next time.